Yeah.
Okay, recording
and recording is progress.
Okay, over to you then.
Have fun. Okay. As usual, you say when you are in a Zoom meeting, can you see my screen? Can you hear me?
Yes to both of those.
Okay. So let's get started. Just a brief agenda. Okay, I will not meet all of this. Okay, I've tried to summarize as much as possible, but it does not fit. Neither 20, another 15 minutes to give 5 minutes to the question and answer. Okay, I think I arrived to present how Secure Boot works on iMX devices, and even if not going so much details, and then probably giving the AOSP stuff for our next meeting or something like that. Let's see how it works. Okay. And there are some interesting stuff to speak about at the end, to side effect on having Secure Boot on a real product, and I hope we will share this this time or the next one. Okay. So just to say a couple, not so much about me, it's everything written in here. What is not written is that I attend to a couple of training by Chris about AOSP. And it was real nice. We learned a lot, and I'm experienced in mostly the low-level stuff about embedded Linux, so U-boot and bootloader and kernel. But we also do a lot of things in Yocto and the AOSP, as you can see here. I just would like to say also that I have some experience in the rest of the IT. So managing Linux servers, for example, and something like that, networking and so on. And I attend to basic certified ethical hacker course. They give me some introduction about it. But anyway, I'm not a security expert. I'm not the kind of guy that you will call for a security audit on your device, on your product, on the wall development and production sequence that you do, because this is a work on its own. And I just would like to say that you have to keep in mind that you have to call a third party, someone that do a security audit on your product during the development, hopefully as soon as possible, and to follow you and to give so that what you implement is the right thing for the kind of product that you do. Okay, something might be outdated. I'm talking about Andrea 6 on an iMX6, but general concepts are still valid. Okay, so the minor details. There are some questions that you ask yourself when you're speaking about security on your product. All these questions come to the end one that say how much we can and we must invest in security for our product. It mainly depends on what we are protecting. Is the software inside there are some kind of software IP that we don't want that the user can steal. There is some, we want to protect the hardware from running unwanted software, or which is the most common case that we will see more in detail later. We want to have some security, some private information stored inside the device that cannot be shared. This is usually something like a credential, keys to access some cloud services and so on. Now, another question that we need to ask to ourselves is from whom we are defending from. It's just about someone, the casual users, they're doing something wrong with the device, so giving the wrong input and crashing the device, or it's just someone that Google for hacking and play some script that finds somewhere, or is something worse, is maybe a cyber criminal, is a government because our product is in some civil critical infrastructure, this depends a lot on how much effort an attacker give and how much money is spent to attack your device. And from the other side is how much money and effort you invest in the security of your device. So we give an example on securing provisioning keys, cloud API keys, something like that. This is usually stored inside the SoC memory. Okay, this is usually an OTP memory that can be written only once. Is not so much big, so you cannot store so much data inside it. And what we assume here is that the main thing that we need to protect is low level. So we need to be sure that the device, the SoC in particular, if you want, execute only trusted and signed firmware. Okay, so the first brick that we put inside the secure boot is executing the right bootloader and only the one that is signed, because it's the one that first protect the SoC memory and the secret that is stored inside it. Then there are some additional level of security that are implemented because we want to protect also high-level software and user software application, APK, if you are running an Android devices. That is somehow trusted, but can be also untrusted if the rest of the system, the operating system, Android in this case, protect from accessing the low-level resources. We won't get too much deep in details in this. This is quite easy to find documentation in how the operating system protect the low level, the access to hardware resources, but we will focus on how to be sure that the bootloader, the first software that is executed, is the one that we provision, the one that is signed. Okay, we need for secure boot. The first thing that we need is that we need hardware support. Okay, this cannot be done just only in software, because we need hardware to validate the first software that is executed. Okay, usually this is done using PKI infrastructure, so a public key infrastructure. I cannot go in details about this. Just wanted to do so that you usually have a couple of keys, one that is private and one that is public. The private key needs to be kept secret, and is the one that he uses to sign the binaries that are provisioned. The public key is the one that he uses to validate the signed binary, to check if they are signed with the right private key. Okay. The subsystem that take care about the PKI infrastructure in the iMX family from NXP is called HAB, High Assurance Boot, is the one that take care about creating all the stuff needed to sign the images, and also the hardware and the software requires to validate the image into the device when they are before running the device. How does sign image work? You start with the basic image. Let's say that here the image, for example, is the first stage bootloader, so the SPR in case speaking about U-boot. And the image is hashed, so you get the hash from the image to have a smaller thing to sign. And this is encrypted using the private key, and the encrypted hash is the one that carries the signature of the image. The signature is appended to the image together with the public key. This is important to know, because the public key need to go together with the image itself. This is different from, example, from the standard PKI infrastructure, where the public key are public and they are given from a different chain of trust outside, usually by connecting to the network. But here you have a limited resource, and you have a small piece of hardware that need to validate. So the public key need to go together with the image. But the main topic here is how to validate this kind of public key that are stored together with the image. And here is where secure boot come in mind. The certificate authority, the one that create the public and the private key, create the hashes of the public key, and this is the value that is stored inside the SOC. So inside usually an one-time programmable memory inside the SOC. This is where it's written. When the SOC start, fetch the image, extract the public key, calculate the hash of those public key, and compare with the ones stored in their own memory. If they match, the public key are valid, are the one that are used from the original certificate authority, and so we can proceed by checking the signature. If not, something failed, the image is corrupted and cannot be run. Once we have validated the public key, we can continue with checking the signature. That is pretty much the same thing that has been done during the creation of the signature. So we calculate the hash of the image. We decrypt using the public key that are together with the image that are now verified. We decrypt the signature, and so check if the hash of the image match the decrypted signature. If this match, the whole image is verified and is valid, it can be executed. If not, well, usually it means that somehow the image is corrupted, and usually what most secure boot devices do is just halt or reboot, and usually you don't see anything on the console, but we come about this later when we wrap up the
Germany ru UK ru chalchi to ଗୋଟେ conference ଟି
okay.
Germany ru chalchi रे ଗୋଟେ କାମ
I just would like to tell you that nothing is perfect.
training kor deyki
Someone with the microphone open, I think. Okay.
मोर Google Pixel रे
Hi, somebody's not.
Somebody has
Google Pixel ପାଇଁ କାମ କର
One second. Okay, Andrea, I muted you, so you'll have to unmute yourself.
unmute. Okay.
Sorry.
Okay. Thank you.
Okay.
I stated before, as software has bug, also silicon has problem, hardware has errata inside it. The problem here is that if your software has bug, you can deploy on field, you can create patches and deploy an updated bug-free version on the field. If hardware has some trouble, especially trouble when you're speaking about secure boot, well, you cannot patch hardware on field, you just have to substitute it. And if the silicon vendor provide a fix, and this is the case. So I put here a couple of references about hardware errata on the iMX6 about the secure boot. So in this way, to make it brief, you can just use a buffer overflow to download whenever a specially crafted binary on the device, and so bypass all the check that we already see. I think I have 5 minutes or so left. 10? No? Okay, well, let's continue.
Yes, about 5 minutes, yes.
5 minutes, okay, I think we
If you
can
could just bring it to a conclusion, that'd be great.
Okay, so HAB setup is quite simple. You just generate the key, and then you can assign the image. There are a couple of scripts that can be used for this, and this is not rocket science, so we can go ahead. What I would like to show here is that you can have both the key and certificate to sign the image and the hash to program on the OTP. This is quite easy to program on the device, thanks to Linux drivers to manage the OTP. Just to say here that you have, once they are programmed, please remember to lock those registers because they are one-time programmable, but you can flip the bit more than once to 0, and so you can just corrupt the device. And when the magic happens is when you program the OTP. So you have in U-boot, you can just have a simple command that show you the status of the secure boot device, the secure boot status. And what is to notice here is just this has not been enabled yet. Secure boot is not enabled at this moment, but the device, once the OTP are programmed, check for the image if it is valid or not. And so the last step will be to lock the device to enable secure boot, but please do this only when you see the message that no hub event has been found, because otherwise you will break the device, because it means that something went wrong. Maybe you programmed the wrong OTP value, maybe you just misuse the signature procedure, because you are not able to produce the right binary that is used that need to bypass need to be validated on the device. Okay, so this is the last step to do only when everything goes fine. Okay, I think from here we start with hanging out with AOSP finally. So what we need to do here is not thinking too much about the high-level stuff. So the data partition is read-write and cannot be handled in this way. Need to be to set up encryption that it also scope here. The system partition is already checked because it has the M-verity on itself, and the signature to start the M-verity is the boot image. So what we need to validate is just the boot image and the recovery image when you are booting recovery. And so, but the boot image is just a big binary, and so can be signed with secure boot as we've seen before for the bootloader and the other part. What we need to implement is to check the image before booting, okay? And what to highlight here is that, as usual, the authentication routine is just a call to the hardware itself. So you say to the hardware, please validate this image. The hardware find the public key, check the public key, and check the signature. And then if everything is successful, can continue to it, okay? The last thing that you have to do is to patch the Android build system to sign the image. Luckily, this is quite simple if you implement a couple of scripts together with CST, and because there are a couple of places, at least this is the right place for Android 6. I don't really know it when for newer releases, nearly the same place. You just call after boot and recovery image are created, you just call the signature or the sign script to sign the image and replace the original images, okay? In this way, this is quite useful, at least in our use case, because without patching some other place, it also generates the OTA, for example, correctly, because OTA is based on this kind of images, okay? There are a couple of additional here that we want, that if I have time, I want to complete.
I think you're out of time, actually, Andrea.
I'm out of time. Okay, maybe we can see, we can wrap up next time the product environment, okay? Because they are quite interesting. Okay.
Yeah, it'd be great to kind of complete the story and look at particularly the integration with the AOSP environment and the images and so on, and how this happens with, or how this is validated with Android at boot time. But let's do that in the next meetup.
Okay. Okay. I think that was enough to come here to see how it fit together with the build and the validation at runtime. Okay.